Hi everyone, welcome back. Today I have an exciting topic. I wanted to make a tutorial on MIMO radar, which I think is very interesting. Okay, so what is MIMO radar? Multiple input. Start with the simple name itself. Multiple output. So this is a very hot topic, I guess, right now. So let's talk about it. Okay, so let's see what it is. So we discussed earlier what is SAR, synthetic aperture radar. Just to give you a brief review, if you have, let's say, a single antenna, you can move it, say, on an XY grid like this, and then you get a 2D array from which you can create, a nice synthetic aperture and then make nice, good quality images, right? On the other extreme, let's say you can have a phased array. Right, where you essentially have, instead of a 2D, instead of scanning in 2D, you have a 2D array itself. Something like this. And each element has like a phase shifter and an amplitude controller, I guess, and an amplitude, it's a modulator, something like that, that it's connected to. You can control the amplitude and phase of each element. And with that, you can create an actual beam rather than a synthetic beam that's narrow. Let's say this is the beam, and you can steer this beam in 2D. So you can use this to also form radar images. We haven't really talked about this, but it's pretty straightforward if you know what a phased array is. At least conceptually, it's straightforward. Of course, implementing it is very difficult, right? So in some sense, synthetic aperture is simple in terms of hardware complexity and signal processing. Actually, signal processing may be harder, but at least the hardware-wise, it's very simple. You just have a single antenna. You don't have any mutual coupling issues. You can move it around and form a nice synthetic aperture. But of course, it's very slow, right? Because data acquisition takes time, and you have to go through all these signal processing algorithms to form an image. Phased arrays, on the other hand, are very complex. A lot of research goes into designing a phased array because you have all of these elements. You can't make this very big. For example, if you want to have about a 1-degree beam, synthetic beam, then you need a 100 by 100 element phased array, which is extremely large, right? It's first of all very expensive. Complexity in terms of hardware management, power management, heat that it generates, and then dealing with this large data set that comes in, dealing with mutual coupling, element failure, all of that is very complicated, right? But of course, it's very fast. It's literally instantaneous because everything is happening in real space, right? You're not collecting and processing anything. You're just applying some amplitude and phase weights, and that is automatically generating a narrow beam. You just take a 1D FFT of that, and then you have your target along that ray, where the beam is, the image along that ray, and you can very quickly, almost instantaneously scan, right? So maybe military and very rich people can afford something like that. It's very nice. And SAR, it's simple. So simple to set up in a quick experiment, but of course it's slow. So the way I think of MIMO is that it's somewhere in between phased array and SAR. And hopefully by the end of this video, you will be convinced that it's somewhat of a compromise. So what is MIMO? So MIMO is if I have multiple transmitters. So let's say these are my transmitters and multiple receivers. So let's say I arrange them like this. So this is Rx. Then what you can do is you can collect data from this kind of an arrangement. We'll discuss how you do that. And you can generate, it's somewhat simpler than phased arrays, as you can see. You don't need the phase shifters. You don't need n by n elements, you need much smaller number of elements. So hardware complexity is simple or relatively simpler. Let me say simpler rather than simple. And it is also fast or faster. Right? So it's faster than that and it's simpler than this. Okay. It's actually a neat idea. So let's discuss it. Okay, so before I dive in, some of the prerequisites, I guess, that I recommend people go over before you. I mean, you'll still understand the concept of MIMO, but to really understand it well, I would highly recommend that you watch the FMCW radar video that I did. And I would also maybe recommend the step frequency radar video or pulsed, it doesn't matter, either of these. And I also highly recommend watching the back projection time domain correlation video, the 3D imaging SAR video, time domain correlation SAR video for 3D imaging. I think if you watch these two and you understand them well, it'll have a much better understanding. But anyways, so in today's video, I guess I wanted to, this is the outline. Right, so we'll start with 1D beam steering to motivate why we would want to actually use MIMO or where it comes from. Then we'll go on to far field MIMO. So we'll use the far field approximation and then kind of establish what MIMO is, why it's useful, what's the idea really. And we'll also establish what is a virtual array. This virtual array concept or equivalent array concept. And then we'll talk about signal diversity that's required in MIMO radar, why it's required, and briefly talk about what kind of different diversity schemes you can use. And then the last is 3D imaging. Using MIMO back projection or time domain correlation, whichever. So in the previous video, I showed that back projection time domain correlation are the same. We won't go into too much detail. I'll just give you a brief derivation of MIMO back projection. So in short, I guess today's video will be more conceptual, not too much math. I just want to introduce the concept of MIMO and what's the idea behind it. If you understood SAR, it should be pretty straightforward to derive the same equations for MIMO. So the main goal is to develop the concept. Okay. With that, let's get started. So 5.1. So let's just look at 1D beam steering. Since I did not talk about this, we directly went into 3D imaging last time. Maybe I should call it 2D beam steering. Okay, let's just say 1D array beam steering under the far field approximation. Okay. So let's assume I have an array of antennas like this, transmitter and receiver. Let's actually just use 5 antennas. Okay. And I'm in some coordinate system. And my target is somewhere far away in the far field here. Sorry. Okay, so I turn on the first element. Since it's in the far field, let me just assume that they're all parallel rays. Right, it goes that way, hits that and comes back. Comes back. Then the second one goes, hits and comes back. Third one goes, hits and comes back. Fourth one goes, it comes back. The fifth one goes, it comes back. Right? Now, let me just review maybe what is far field approximation, right? So if I have some antenna here and I'm looking at some target that's at some target vector position R, and we've used the convention R prime for the element location, then the distance from the element to the target is R minus R prime. This is the vector, right? Just from basic vectors. And the distance is modulus of that. So the far field is defined to be, I mean, not defined necessarily, but when you are in the far field, you can approximate this distance R minus R prime as R minus R prime dot R hat, right? Where this R is just the modulus of this vector, and this R hat is R divided by the modulus. That's just the direction in which it's going, right? Okay. So if you assume that was the origin, this is the origin, then the phase front is sort of like this. Let me draw that. Let's say that's the phase front. That's the zero phase reference. Then this is R prime dot R hat. It's the same for this one, R prime dot R hat. And if I assume this distance is D, then it's easy to show that R prime dot R hat is just D sine theta, where theta is this angle. Right? So if you want to look at a target at an angle theta, if you want to steer the beam rather to an angle theta, then this extra phase that you will see at different targets, at different element locations, is given by R prime dot R hat, which is D sine theta. So for a phased array, if you want to if it's a transmitter phased array, you want to focus the beam along some direction, then the phases that you need to apply are basically this R prime dot this D sine theta. Right. So here it would be 2D sine theta. This would be D sine theta. D sine theta. This would be minus D sine theta, and this would be minus 2D sine theta. Right. But anyways, now that we're talking about like the radar, let's not go into phased arrays. So in this case, since each element is looking at it at a given time, we end up with this sort of formulation, right? So the measured signal at each element using the generalized signal model, which we developed in the previous video, is e to the minus 2jk mod r minus r prime, which is e to the minus 2jk in the far field, minus 2jk r prime dot r hat, which is nothing but e to the minus 2jk r e to the minus 2jk nd sine theta, where n belongs to minus 2, minus 1, 0, 1, and 2, right? So for simplicity, I'm going to call the phase phi to be kd sine theta, or nkd sine theta, Pn. So basically the nth element sees an additional two-way phase of 2 phi n. Right? Since it's two-way, tx has phi n, and then rx will have another phi n of phase, so it's 2 phi n, which is 2 nk d sine theta. Right? So it's pretty simple now, since you have these measurements and each of them, your measured signal is basically e to the minus 2jk r for the nth element, let's say, times e to the minus 2 phi n or 2J phi n. If you want to form an image, steer the beam and form an image in post-processing, all you need to do is take these measurements and then multiply with 2J phi n and then sum over f. Right? So this is basically the far field back projection of beam steering. Digital beam forming, it's called many different things like this, but that's what it is. Right? Okay. So this picture is really important. Now you may say, okay, since I have 5 elements, why should I only look at the signal that goes out here and comes back here? Why can't I look at the signal that goes out from here and comes back to this one? Goes out, comes back to this one, goes out, comes back to that one. What about all those signals? What happened to those? So the question that we now have to ask is, since we have TX and RX element and it's not a synthetic aperture, let's say it's a real aperture, I have these 5 elements that are physical. Of course, in synthetic aperture, you can't transmit from one location and look somewhere else, right? Because you're transmitting and receive at a single time. But if I have a real aperture like that with 5 elements, which each of them has TX and RX capability, then can we use the cross coupling terms, right? So the question is, if each element has both transmitter and receiver, can we also use I'll just call it the cross terms. The more technical term would be the multi-static, bistatic signals. It's not good to say cross terms signals. I'll just say cross coupling, maybe. It's coupling signals or multi-static signals in the reconstruction or in the image reconstruction. Okay, and the answer is yes. You can, but need to be careful, let's say. Need to have clever design, I'll call it. Can't just do it the way I have it up there. And that's the idea behind MIMO. Okay, so before we get into MIMO, let's talk about MISO, I guess, which is multiple input, single output. For simplicity, we'll start with this. Okay, so what do we have here? So let's say we have, again, coordinate system, something like this. I have, let me use purple for transmitter. Let's say I have one TX and I have 4 RX antennas. So I've separated the TX and RX. We'll deal with the case where they are equivalent later. Okay, again, I'm looking in the far field. So let's say I'm looking at some target that's out along some direction theta. Right? And I want to know what the phase difference is for each signal. Right? So it's pretty simple again. So what I'll do is I will mark let's say that's the first phase front, second phase front, third element, and fourth element, right? Okay. So now let's see. For the first RX, this is 1, 2, 3, 4. The signal goes out, hits the target, and then comes back to this point. But that's the same thing as coming back to this point, right? So that means that the first signal has a phase delay. Let's call this D1. And I'll call this distance D, right? So that means that phi1, which is the first signal, uh, the amount of phase that is missing, I guess, from from the two-way return is kd1 sine theta, right? Which is this one, kd1 sine theta, right? So that is basically the signal received, the retarded phase of the first receiver, right? The retarded phase for the second receiver would be a d1 plus d sine theta. And of course, for the third one is a times d1 plus 2d sine theta. And for the fourth one is k d1 plus 3d sine theta, right? So that's pretty simple. If you know these values, since d1 is anyway common, all you need to do is you just compensate the difference values, right? So you just compensate, in the previous case, we compensated this phase, which was 2j phi n. And in this case, you do the same thing, e to the 2j phi n. And you can do nice beamforming similar to the previous case, right? So you take your measured signal and you just compensate these phases and you sum, and that'll give you your image. So this is nice. I mean, here I don't need to have 4 different transmitter receivers. I just need one transmitter and 4 separate receivers, right? And you can you don't have to do any switching, nothing. Just transmit from 1, receive from 4. So that's a nice MISO case or MISO case. But let's say I want to add a second transmitter, right? So now we're delving into actual MIMO. And I'll call this naive MIMO. We'll see why it's naive. Okay, so we repeat the same thing. So now let's say I have, this is my coordinate system again. I have one TX here, TX1 I'll call this. And TX2. And let's say I have 4 receivers. And the spacing here is D. And so the spacing here is also D. And just for simplicity, I'll generalize it a little bit. I'll say this is D1, like the previous case, right? Once again, we have these signals propagating out this way and then coming back with these 4 elements like this. So now what we want to do is again look at the retarded phase for each receiver, for each transmitter. Okay, and it's pretty simple. You can pretty simply see that for phi, let's say from transmitter 1 to receiver 1, I'll call this 1, 2, 3, 4. So that is just the distance between them, right? So that would be k d plus d1 sine theta. Phi from transmitter 1 to receiver 2 is k d plus d1 plus d again sine theta. So that is k times d1 plus 2d sine theta. Page phi 3 1 is from transmitter 1 to receiver 3. So you have to account for this distance, right? And that distance is nothing but k times d plus d1 plus 2d sine theta. which is nothing but k times d1 plus 3d sine theta. And of course, phi 4, 1 is k times d1 plus 4d sine theta, right? Now you do it for the second transmitter. So first receiver, second transmitter is k times this distance, right? And that's just d1 sine theta. Phi 2, 2 is k times d1 plus d sine theta. Phi 3, 2 is k times d1 plus 2d sine theta. And phi 4, 2 is k times d1 plus 3d sine theta. Right? So looking at these signals, it should be pretty obvious that there is some redundancy, right? So for example, this and this are the same, right? This and this are the same. And this one and this one are the same, right? So essentially you've made 8 measurements. 8 measurements. 1, 2, 3, 4, 5, 6, 7, 8 measurements. But only 5 are unique. Right? So that's bad. Why did that happen? I mean, that happens because this D is the same as this D, right? If we can change this D, then we can avoid this problem. And that's the idea behind MIMO. So I'll call this MIMO, but now it is smart. The smart way to design it. Right? So I go back to the same arrangement again. So let's say I have now my 2 transmitters. I'll make this distance 4D. And these are again separated by D. And let's say this is D1. Okay. Again, we go through the same exercise. I'm just going to do it quickly now, I guess. It should be straightforward. Go through these. We look at what the phase front is. And I'll call this number 1, number 2, and this is 1, 2, 3, 4. Right? Then phi 1, 1 is k times d1 plus 4d sine theta. Phi 2, 1 is k times d1 plus 5d sine theta. Phi 3, 1 is k d1 plus 6d sine theta. Phi 4, 1 is k d1 plus 7d sine theta. Right? And then you can do the other ones. Phi 1, 2 is k times d1 sine theta. Phi 2, 2 is k d1 plus d sine theta. Phi 3, 2 is k d1 plus 2d sine theta. Phi 4, 2 is k d1 plus 3d sine theta. So now you should be clear why I chose 4d to be the distance between the 2 transmitters, right? Because the second element ends at 3D. So you want to start the next one 4D. The second transmitter ends at 3D, so we're going to start at 4D, right? So this way, essentially what we've done is we've made, a transceiver or a system that's equivalent to having a single transmitter and 8 receivers, 3, 4, 5, 6, 7, 8, right? So if this distance, let's say, So if this distance is D1 and this distance is D, then it's pretty straightforward to see that you would get exactly the same signals from these two, right? So what's the conclusion? The conclusion is that an M by N MIMO system is equivalent to M1 by N MISO arrays. But the neat thing is that, if you have M1 by N MISO arrays, you have M times N elements, right? So this one has M times N elements, whereas this one has M plus N elements. Right? So essentially we've reduced the number of elements that we need. Right? And you can actually see that right here. So here, for example, we have 8 receivers and 1 transmitter, which is 9 elements. Whereas here we have 4 receivers and 2 transmitters, which is 6 elements. So to an order, at least to an order of degree, it's about what we're talking about here is that we've reduced the number of elements, right? For example, 9 minus 1 is 8, whereas 6 minus 2 is 4, which is essentially what we've gained. Okay. So let's look into this a little bit more. And let's talk about virtual array equivalency. So what is this? Right. So we saw that, okay, if I have 2 transmitters and 4 receivers, is equivalent to having 1 transmitter and 8 receivers. But how do you actually design something like that, right? Is there like an easier way rather than to go through all this calculation of phi and then coming up with the array positions? There is actually an easier way. So let's take an example to see that. That's the easiest way is to take an example. Again, 2 transmitters, 4 receivers. And we saw that this was equivalent to having 1 transmitter and 8 receivers. And the way you can arrive at this is to take your 4 transmitters, copy, and then paste them at each of your transmitter locations. Take your 4 receivers and move them to each transmitter location. So since I actually have these 2 transmitters, let me move them here. So I have 1 transmitter here, 1 transmitter here, and the separation was 4D. Right. So now when I move my receiver array, I'll move it first here. And then another copy. Let's see here. I need to, the spacing was not exactly right. Okay. So let's see. So this is 4D. And you can kind of see that, right? Like this is D, this is D, this is D, this is half a D, and this is another half D. So that's the 4D. Right? So it's like essentially moving your receiver onto each transmitter location. So mathematically, This is also equivalent to moving your transmitter to each receiver location. So let's do that as well. So let's say I take my transmitter. Okay, and then I move it to each receiver location. What do I get then? The first one would be there. The second one would be there. Third one would be something like that. And the fourth one would be something like that, right? So this is again an 8-element array. Sorry, 8-element array. So you can do either one. You can say it. You can move the transmitters to the receiver or the receiver to the transmitter. So if you remove the receiver to the transmitter, what do you end up with? You end up with an equivalent array that has 8 transmitters, 8, and 1 receiver. So essentially, it's like having a virtual array that's this big. So this is the virtual array. And we saw that, at least in the example above, I didn't really prove it, but it should be easy to see that these two will have equivalent signals. So the signal model or the signals that you receive will be equivalent. Right? But it's much easier to analyze a virtual array that's like this rather than to see, okay, what kind of beam width, what kind of array pattern would I have for a MIMO array. So all you have to do is just take your receivers, move it onto each transmitter location, and that will give you an equivalent array. And your final beam properties will be defined by that equivalent array. So mathematically, actually, this is a discrete convolution. Between TX and RX arrays. So what does that mean? I mean, a convolution is just that, right? It's you take one signal, you flip it over, and you move it to each location of the other signal. And if you have, and you add it up basically, but yeah. So if you have, a delta, you can treat mathematically, you can treat this as a delta function, 2 delta functions, and this is 4 delta functions. So when you convolve these two signals, what do you get? You will get 8 delta functions. Right? The convolution of these two will give you this. So that's the simplest way to think about MIMO arrays. So when you're going to design a MIMO array, what you want to think about is this. And that intuition is very important. So let's take some examples, right? That's the best way to, I think, learn this concept or to internalize this concept. Okay, so let's say, I have 3 transmitters like that, 4 receivers. So now I want to find, okay, what is the convolution between these two? Sorry, convolution between these two. So I'll do it both cases. So let's take first the receivers onto the transmitter case. So I select this, copy. So I paste once like this. And then there's one sort of maybe up here. And then another one that's here. Right. So now I basically done this way. Sorry. So this is convolving this onto this. Now we will convolve this onto this, which is take this, copy, paste. So I have one like that, one above that, one to the right, and one below that. Right, and you can clearly see that these two are exactly the same. So the question now is it a good design? Is it a good design? It's not a good design, right? Because you see that we have a redundancy here. Two elements are falling on top of each other, which is not good. Right? Ideally, what we want is we want each of them to be completely separate. So you don't want any redundancy. So let's take another example. So let's say they're equivalent. So let's take another example. Let's take one that actually works. So here, I mean, although I did the previous explanation and everything in 1D, whereas here I'm using sort of a 2D array. But it's pretty straightforward to see that this convolution applies in the X in each coordinate. So in X coordinate and Y coordinate. So essentially you have to do like a 2D convolution, right? So it also applies to 2D arrays. That's pretty straightforward to see. So let's take another example. So let's say I have 4 transmitters like that and 4 receivers like this, right? They're all equally spaced. They don't have to be unequally spaced. So let's say this is D, this is also D. Since now we are in 2D, equal spacing will be okay. And let's see why that is. So it's pretty straightforward. Let's say I take my receiver and now I'll move it onto each transmitter location, right? So there's one like that, one next to that, another one next to that, and another one next to that, right? So that's the Rx onto Tx. And we can obviously do the same thing for the other case. Take the Tx array. And so we need one up there. I mean, I guess I didn't draw it equally spaced, but let's assume they are equally spaced, right? One down there, down there, and one down there. So again, you can see you get the same result. Of course, my drawing ability is not great, so they look like they're not the same, but they are equivalent. So this is nice. So you've had 4 transmitters and 4 receivers, and you got 16 elements in your virtual array, which means that it's a good design, right? No redundancy. So that's why this is sort of a popular architecture for 2D arrays. And here you can also see that just from taking 2n elements, you have gotten a virtual array that's of size n square. And that's a big improvement, right? So your hardware complexity is reduced by almost an entire order of magnitude. So instead of 100 by 100 elements, now you only need, so for a 100 by 100 array, virtual array, you would need 10,000 elements, whereas now you only need 200, right? You need 100 plus 100 instead to get the same resolution, same signal diversity, basically, right? That's a huge improvement. Let's take one more example. Let's say I have 8 transmitters that are arranged like this and 4 receivers and 8 receivers. Okay. So 8 transmitters, 8 receivers arranged on the sides of a square, right? So what does the equivalent array look like now? This is more interesting, I think. So we need to take the entire receiver. Okay, let me do it this way, actually. So just to make it easier, I'll first take the transmitters, copy, paste, and now I'll move the entire receiver block onto each transmitter. So this is sort of more explicit. Paste. Okay, so we center it on the first transmitter. Let me just erase this stuff. Then we center it on the second transmitter. Then we center it on the third transmitter. fourth. And then we go down, center it on this one. Next one. Next one. And the next one. This is very nice, right? Now what we've got is impressive, in fact, because now this one's aperture size was D by D, let's say, or I guess 3D by 3D. The spacing is D. Whereas this one is twice as big, right? 1, 2, 3, 4, 5, 6, 7, 70 by 70 aperture size. It's almost twice as big, right? Actually, it is twice as big, more than twice as big. So essentially what we've done now is the array size is also doubled. Right? So we've only used an area of L square, but we have a virtual array that has an area of 4L square, which means that the resolution, angular resolution, is halved. And remember that this whole thing inside is empty, right? So we filled up the area. Not only have we filled up the area, we've also augmented the size of the array, which is very nice, right? And that's why this is also a very widely used uh, architecture for MIMO arrays. Okay, so let me leave you with a quick question, I guess. So here we've only discussed the case where, the TX and RX are separate, right? So this is a TX, or I guess this is RX, and this is the TX. So what if, I give you a problem to think about? So let's say you go to the store and you purchase 100 TX, RX, TR modules, right? Which means that each one can act as a transmitter and receiver. Then it should be clear that since, for this architecture, if I have this as the TX and RX, and this also has TX and RX, you can't get better than this, right? Because the convolution would end up the same. So you have a redundancy factor of 2. You essentially have 2 arrays on top of each other, right? Because the first case you can take this to be TX, this to be RX. In the second case, you can take this to be TX, this to be RX, and you end up with the same array, which means that you don't want to arrange them on the edges of a square, right? That would have a redundancy factor of 2. So let's say you end up with purchasing 100 TX or TR modules. Then what is the best MIMO geometry for highest signal diversity or lowest redundancy? Right? So how do I arrange these 100 elements so that when I convolve it onto itself, or self-convolution now, because the TX and RX arrays are identical. So if I do a self-convolution, how do I end up with the best? What kind of array do I choose so that the self-convolution has the largest number of elements? That's something to think about in 2D arrays. Okay. So hopefully that kind of makes clear what is the general idea and how MIMO works in the far field. I should add that as a caution. Let's do it in my page. So caution is that this concept of virtual array concept is only valid in the far field. Or at least let me say I showed it to be valid in the far field. I did not show that it's not valid in the near field, but indeed it is actually not valid in the near field. Is only valid in the far field. So if you want to analyze the performance of your MIMO array in the near field, must rely on the point spread function. We covered what that is in the previous video. So essentially you look at what the radar image of a point target looks like with back projection, for example. We'll talk a little bit about back projection at the end today. But yeah, you want to look at a point target, see what it looks like, and then from that you can estimate what the effective aperture is, effective beam width is. But this virtual array concept starts to fail when you're very close in the near field. Okay. So hopefully the virtual array concept for MIMO radar is pretty straightforward now. Understand it well. So let's talk about one thing that I've sort of glossed over, which is signal diversity. So what does that mean? So I said that, okay, if I have multiple transmitters and multiple receivers, then, you can send signals from these guys, and then it hits the target and comes back to these antennas, right? But the important thing to note here is that you can't simultaneously transmit the same signal from both transmitters, right? Otherwise, what happens if you look at the phasor diagram, right? Let's say this is the target. This transmitter signal goes and hits it. Another transmitter signal also hits the same point. So the wave that is scattered back is essentially the scattering of two phasors, TX1 phasor and the TX2 phasor, that add up. These two transmitted signals add up at this point, and that gets scattered back. So essentially, it's like almost like you have just a single transmitter, right? So you can't transmit the same signal at the same time from both the transmitters. And that's why you need to do some kind of multiplexing, right? So TX signals must be multiplexed. What does that mean? So multiplex just means that they need to be separate. So they can be separated using different schemes. So they can be separated in time. That's called time division multiplexing, right? Where you transmit this signal, you receive all four or all five, and then you transmit this, and then you receive from all of these. So then you can separate the two transmitted signal, uh, the two measurements basically, right? And that's nice for FMCW. That's somewhat popular for even, for example, if you have just a network analyzer and a microwave multi-port switch. So you can just switch between the two transmitters and the two receiver and all of the receivers and collect your entire signal matrix, right? Okay, that's time division multiplexing. Or you can also do, OFDM. Uh, OFDM is the term that they use in MIMO communications, but even in MIMO radar, there is something similar to OFDM. You can use orthogonal signals. Or if you're doing pulse radars, you can do code division multiplexing. So you can have different codes on these two transmitters, and then you can collect the signals and then separate them in post-processing. And you can also use something called orthogonal chirps. So that's another thing. I won't go into too much detail now, because that would require a separate video. But orthogonal chirps are basically two chirps that start at slightly different frequencies, right? And you can actually show that even if the frequencies are slightly different based on the bandwidth, if it's a very wide band, then those two chirps would be orthogonal. So yeah, so you can separate the two signals pretty well. Okay, so essentially you just need orthogonal signals. So that's something to keep in mind. Maybe I'll make a future video on different multiplexing schemes, but conceptually that's what it is. Okay, so with that sort of concludes the conceptual part. I'll end with sort of the back projection for image formation. And this is true. So we saw, for example, for far field, if the target's in the far field, all you need to know is, the phi n component, phi n for different Tx and Rx. So I'll call it phi nn, right? So if for the nth transmitter and nth receiver, if you know what the geometric positions are in the far field, it's easy to steer the beam in that direction, right? You just compensate that phase and you add up the signals. But let's say you're in the near field, then this whole idea of equivalent phase or that far field approximation which gave us this phi doesn't work, right? So how do you do image formation when you have a MIMO array in the near field? So we can develop quickly back projection or time domain correlation, whatever you want to call it, for MIMO imaging. This is more popular in the near field. And typically you would be in the near field if you want to do very high resolution imaging using a very large array. So that's why it is important to look at near field imaging. Okay. So since I already discussed at great length back projection for SAR, I won't spend too much time developing the intuition behind back projection and time domain correlation. I showed in the previous video that mathematically back projection, time domain correlation, delay, and sum imaging are all mathematically equivalent. So in this case, we'll just deal with one of them, back projection, and I'll develop it more quickly. I highly recommend that you watch the previous video if you want to get a deeper understanding. So let's say I have my transmitter here, call that RT, this vector, and the receiver is somewhere here. Let's call that vector RR. So I'm not making any assumptions on the geometry. They're just arbitrarily located. And let's say I'm interested in focusing, or let's say I have a target at some position R. Then we know that this vector is R minus RR. And this vector is R minus RT. Right? So then the two-way signal that I receive is, so let's say as a function of the position of the target, position of the transmitter, position of the receiver, and K, which is the wave number, is f of R, which is the reflectivity function as a function of R. So at this point, it has some reflectivity. At this point, it has a different reflectivity. And we define more clearly, more explicitly what exactly this reflectivity function is in terms of the RCS in the previous video. So I recommend you go watch that. Here, of course, this would be the bistatic RCS rather than the monostatic RCS. If you don't know what that means, that's okay. It's just saying that RCS is not exactly the same when you look from two different angles, whereas when you look at the same angle. Anyways, so you can show that this f of R is related to the bistatic RCS. But for now, for imaging, just treat it like some kind of reflectivity function. If you're curious, you can watch the previous video to get a better understanding of that relationship. Okay. So there is one phase which is picked up in this propagation, which is K times R minus RT. And the other phase is picked up in the backward propagation, which is minus JK mod R minus RR, right? And we showed that also that there is an amplitude factor as 1 over R because of the decay in the electric field from propagation. So this is the simplified signal model for a single target. And the actual measurement that you make is SB tilde, let's call it, is an integral over all points of the target, basically the entire R position vector of this signal. Right? So this was for the single target. If you have an extended target, then you end up with this. So this is the actual measurement that you make, right? And we discussed all this at great length in the previous video, so I'm just doing it quickly now. dx, dy, dc. So we showed that for back projection, all you need to do is just compensate this phase and sum it up, right? So in this case, the expected target reflectivity or the estimated target reflectivity is simply given by summation over k, summation over RT, which is actually two summations over x and y. Actually, no, it's only one summation. My bad. RR SB tilde, which is the measured signal, times e to the jk mod R minus RT, which is the inverted phase, R minus R. That's it. So this is called the steering matrix. This is the steering matrix. Explicit is equal to square root of x minus xt square plus y minus yt square plus z minus zt square, which is 0 based on the coordinate system that I've chosen. But of course, if you have zt as well, you can put it in there. R minus rr is square root of x minus xr square plus y minus yr square plus z square. Right? So your signal would be a function of the x position, the transmitter position, the receiver position, and frequency. This is also a function of transmitter position, receiver position, and frequency. You multiply those two matrices, and then you sum over all the components, and that gives you the reflectivity function at a single pixel xyz. You do it all over all the pixels of interest, and that would give you your estimated radar image. So, I mean, if you understand SAR reconstruction, it's basically the same. It's sort of a generalized version of SAR reconstruction. So I went through it fairly quickly, but that's the idea. Now, the next question is, I said that for SAR, this is very slow. Of course, even for MIMO, it would be slow because it's the same thing. Can we speed it up? And the answer is yes. You can speed it up. Back projection otherwise is very slow. So with that, let me just quickly conclude. What are the advantages and limitations of MIMO? So the big advantage is that it's very fast data acquisition, right? Assuming that, okay, you have an actual aperture, you can also do MIMO as a synthetic aperture. You can place the transmitter and receiver on two linear stages. You can move the transmitter on this, receiver on this, but you don't really get any speed improvements really, because you have to stop the transmitter and then collect all the receiver positions, then move the transmitter, then again collect all, then move, then again collect all. So typically MIMO is not done as a synthetic aperture. It's a real aperture. You can also even combine SAR and MIMO. So you can have, for example, you can have 4 transmitters, 4 receivers. You collect all of this data, and then you move this whole thing there. Then you collect all the data there, and then you move it here. And you collect all the data and you move it here, and so on. So you can do these combinations. They're called SAR MIMO, combination of SAR and MIMO, to sort of lie somewhere between. In the beginning, I had started with saying that, okay, MIMO is between SAR and phased arrays. So you can kind of move along this anywhere in between these two by doing a combination of them. Okay, so the data acquisition is fast, but what about processing? Of course, back projection is very slow, but as it turns out, you can also use fast reconstruction using range migration. And I will present that in a future video. Then a big advantage, of course, we saw is that the number of elements are vastly smaller than a phased array. So you go from n square roughly to n, right? And you also don't need the phase shifters and so on. You just need some switches or some signal diversity. And we also showed that you get a higher resolution, in fact, from the same aperture, right? And that's a big improvement, in fact. which you don't get from phased arrays. So twice the resolution or half the resolution. You also get some mutual coupling improvement, right? Because now, for example, we saw that the TX separation can be much larger than the RX separation, right? So the coupling between this and the mutual scattering between these two will be small, right? So that's a good thing. Isolation will be large and also the coupling will be small. Of course, you still have mutual coupling in here. And if that's a big issue, then you can maybe do something like 2TX and then 4RX that are separated. You can play around with that. So that gives you some flexibility. Okay. So these are all sort of, but okay, let me just say that there is still mutual coupling. For synthetic aperture, we saw that there is no mutual coupling, right? Because you have only one element at a time, really. So there's no such thing called mutual coupling there. Okay, the next thing is complexity is somewhat moderate compared to phase arrays, right? So you still need the signal diversity in the transmitters, and you still need maybe some kind of, either in terms of by using switches or by designing your transmit pulses correctly, so you don't completely get away. But still, the number of elements are reduced and you don't need the phase shifters. It's easier to handle power and so on and so forth. So in that sense, it's better. So hopefully that gives you a good intuition of MIMO arrays and MIMO radar, why it's useful, why it's become so popular, especially for automotive, it's very popular. So with that, I would conclude. Just to give you a heads up, I said that in the previous video, I said I'll make an HFSS and MATLAB tutorial for SAR, but I delayed that, I guess, for now, because I want to do it for MIMO as well. So I thought first I'll explain MIMO radar and then I'll do that. So I'll come up in the next video, we'll do an actual demonstration using HFSS and MATLAB for both SAR and MIMO together using FMCW signals. So how do you generate a data set and actually do image reconstruction of, let's say, a real world target or some synthetic target using HFSS signals? First, we'll do like synthetic data generation in MATLAB, and then we'll use HFSS to generate a data set and then reconstruct the image from that data set. And then after we're done with that, that'll sort of conclude the slower, greedy algorithms. Then we'll move on to fast reconstruction algorithms. So that would be range migration, omega k, frequency wave number domain, wavefront reconstruction. They're all basically the same thing. Holographic reconstruction is another name that's commonly used, and so on. So we'll discuss all of these. So that's what's upcoming. Hopefully you're looking forward to that. With that, thank you so much. If you have any questions, you can leave them in the comments or reach out to me via email. So have a nice day.